I'll start.
All right, Bismillah ar-Rahman ar-Rahim. Today we are presenting the aircraft control systems, the altitude control. This is group number 4, right? Next slide. This is our group members. My name is Nuruddin Hani Abdulaziz Abdul Maqsood Al-Deeb, matric number 209586.
My name is Marwan Muhammad Magdi. My metric number is 208650.
And my name is Anbu Chandra and my metric number is 213622.
Hi, my name is Ahmad Harisaka bin Ahmad Rizmi and my metric number is 210252.
Hi, my name is Fadiba Elahim and my matrix number is 200928.
Okay, so let me go for the introduction first. So actually we have choose for the altitude system control as the part of our research. So the introduction is the modern aviation industry relies heavily on sophisticated control system to ensure the safe and efficient operation of aircraft. So among these systems, altitude control is a critical aspect for an aircraft's flight control system. Altitude control systems are designed to maintain or adjust the altitude of an aircraft according to the pilot's command or preset flight plans and ensuring the smooth and precise vertical movement during various phases of flight, including takeoff, cruising, and landing. Next slide.
Okay, so I'll be discussing the altitude control system in aircraft, which is essential for maintaining precise altitude during flight. The system consists of several critical components, which are sensors, controllers, actuators, and feedback loop. First of all, sensors such as altimeters, accelerometers, and gyroscopes provide real-time data on the aircraft's altitude, vertical speed, and altitude. Next, the controller processes this sensor data and determines the necessary control inputs. Controllers can be various types, including proportional derivative, PD, proportional integral, PI, or proportional integral derivative, PID controllers. Actuators will then execute the commands from the controller by adjusting the position of the control surfaces like the elevators and modulating the engine thrust. Finally, the feedback loop continuously monitors and adjusts the altitude, ensuring that the aircraft responds accurately to environmental changes and pilot inputs. Okay, next.
Okay, so this is the equipment used. Okay, so usually this is quite a simple altimeter that used for the altitude control. So the first one is 8030 electronic altimeter. Okay, so for the second one is the barometric pressure, the altimeter which are included for the barometric pressure, altitude measurement, and aviation. Next slide. So this is the example of the block diagram for the altimeter. So this block diagram is quite complex block diagram. However, it still contain of the important parts for the altimeter control, which is it has the controller, it has the receiver, it has the actuator, sorry, and also it has the feedback. So this kind of particular components of parts have fully what we call it as fulfill the function of the altimeter. So next slide.
Okay, so I'm going to present the input of the control system. So there is a 4 input of the control system. The first one is a reference signal. The second one is a feedback signal. The third one is a external disturbance, and the fourth one is a control commands. So regarding the reference signal, so it's a desired values for the system output such as a position, velocity, and orientation. The purpose is the signal defines the goal for the control system, indicating what it should achieve the term of the altitude. The second is a feedback signal. So feedback signal is a real-time data gathered from like a gyroscope and the accelerometer as explained earlier. So the purpose is similar like for the reference signal, which is this signal allow the system to dynamically adjust the correct any error, ensuring the accuracy and reliability in meeting the desired altitude. The third one is external disturbance, which is the unpredictable environmental factor, including wind and obstacle. So the purpose for the external disturbance is the control system must identify the the counter this disturbance in a real time, maintain the stability and the performance. Third one is a control command. The control command is the output from the control algorithm, so that are sent to the actuators. So the purpose is because this command ensure the system achieve its performance and objective by providing a smooth and precise adjustments to maintain the desired altitude. So all over the overall, so the reference signal, feedback signal, the external display, and the control commands are critical input for an altitude control system. They work together to ensure the aircraft or the spacecraft maintain the desired altitude accurately and reliability despite any environmental changes will be happen to the control system. That's all from me. Next slide.
So when it comes for the sensors that are integrating the aircraft control systems that come, there's so many of them that come from many different subcontractors, but like the main ones are for the accelerometer and the altimeter and the gyroscopes that we're going to talk about. So these like provide the real-time data for like maintaining and adjusting the aircraft during like different flight phases, like the takeoff, cruise, and descent, and so on and so forth. So like by integrating these sensors, like the control system, like it makes sure of like these accurate readings and monitoring and response. So let's go on for the first one, the accelerometer, where it like measures the acceleration forces along like different axes, and it also provides like data for the rate of change of the velocity. So like this kind of information, it's important and like to change and like monitor for this control actions and to make different adjustments for the aircraft's movement and to like ensure like the smoothness for like precise altitude control. Next slide for the altimeter. So it's responsible for like providing the altitude readings by measuring like different atmospheric pressures, similar to like the pitot tube, where it detects with a tube. So the altimeter's output serves as like a key input for the control system. So it enables it like to compare of the current altitude with the one that you want, like the desired point. So this comparison, it kind of generates like an error signal used to like adjust these control inputs so you can maintain the aircraft's altitude into like a more accurate way. Next slide, we're going to talk about the gyroscope, where like it measures the angular velocity around the aircraft axis. So it gives like this orientation data. It's like important for like maintaining and correcting the aircraft's attitude. So this kind of information, it helps like stabilize the aircraft and like ensures the accurate altitude control by like contributing like to the feedback loop that continue like it monitors and adjusts the altitude in response for like the real-time data. That's all for me.
All right. So as for the control strategy for our project today, what is a control strategy? It's an altitude control system which is pivotal for maintaining the desired altitude of an aircraft during various phases of flight, such as takeoff, cruising, and landing. This involves managing the elevators on the tail to control surfaces and engine thrust based on real-time data from various sensors. The altitude control system uses, as explained earlier, PID control, which is an approach that is used due to its simplicity and effectiveness in achieving desired system behavior. So for our strategy, we're going to be using the PID controllers. which is employed by most altitude control systems. These adjust the aircraft's control surfaces and thrust to minimize the difference between the desired altitude, which is the set point, and the current altitude or the cruising altitude. Down, I've just written a couple of definitions on each term of the PID controller, but we can move on to the feedback loop. Sorry. So sensors include altimeters, accelerometers, and gyroscopes, just as explained by Marwan earlier. The sensor data is continuously fed back into the controller to compare with the desired set point, and then the error signal generated from this comparison is used to adjust the control inputs. So handling the inputs and outputs of our control strategy. Also, as explained earlier, the reference signals desired altitude and other parameters set by the pilot or preset flight plans. The feedback signals, they are basically real-time sensor data that informs the controller about the current state of the aircraft. And the external disturbances also count as an input, which is the environmental factors such as wind be counteracted in real time. As for the outputs, commands sent to the actuators to adjust the aircraft's control surfaces and engine thrust. So what are the advantages of this specific control strategy is that the PID controller strategy provides high accuracy in maintaining the desired altitude by continuously adjusting the control surfaces and thrust based on real-time feedback. The stability, where the derivative component of the PID controller helps in damping oscillations, contributing to the overall stability of the aircraft. And then the adaptability of the strategy, which is the feedback loop, allows the system to dynamically adjust to changing conditions and external disturbances, ensuring smooth and safe flight operations.
Okay. In conclusion, altitude control systems play a vital role in modern aviation, ensuring both precision and safety during flight. These systems are indispensable as they precisely manage and adjust the aircraft altitude, integrating key components like sensors, controllers, actuators, and feedback loop. A particularly effective aspect of altitude control system is the PID's control strategy. This approach manages elevator control spaces and engine thrust to maintain desired altitude profiles. Moreover, the PID control strategy's ability to quickly respond to pilot inputs and adapt to environmental changes is crucial for maintaining aircraft stability. And overall, the system significantly enhance the reliability and efficiency of aircraft operations by providing precise altitude control and adapting to dynamic flight conditions. Next slide. And this is for the 2 minutes Q&A sessions and the list of references. Okay, that's all from us. Thank you.